Very good afternoon, students. I hope I'm clearly audible to all of you. Could somebody confirm?
Yes,
Yes,
ma'am.
ma'am.
Thank you. Thank you so much. So, for this session, this is my first class with you all, and for this semester, I am going to teach formal language and automata theory. So, before starting the subject formally, I would like to clear one thing that why are we even learning this subject? Because there's a lot of dilemma about this subject, this particular subject. Often, even after covering the entire course, students fail to understand the utility of the subject or why were they even learning the subject. Okay, so I don't want that thing to repeat actually. So I will try my level best to make the importance of the subject clear before we start learning the subject as a whole, and then we'll uh, get along with it, right? So see, basically, let me share the screen and it will be easier for me. Otherwise, just a second. Yeah. So I hope the screen is visible. Yeah. So, see, whenever we talk about formal language and automata theory, it is inherently related and connected to compilers. If you look at this picture on the top right hand side of my screen, I have three sets, one for formal language, one for compiler, and the other for programming languages. Now, computer science and engineering students can relate directly to programming languages because you are always, after learning new programming languages, may it be Python, Java, anything, C sharp, so you can connect yourself to learning programming languages. But how is automata or formal language and automata theory related? So whenever you are learning a programming language, you are writing a program, you need compilers to compile the program, right? So here is that set for compilers, and compilers for their internal working or functionality take the help of formal language and automata theory. When you will learn the subject compilers in your later semesters, you'll see there are different phases for a compiler: lexical analysis, syntactic analysis, semantic analysis. So in all these phases of compilation, the concept of automata theory is used, and it is an inherent part of compiler design. Okay, so this is one reason, this is one very important reason why we should be well acquainted to the concepts of formal language and automata theory. Secondly, whenever you are you are going for research, you want to design a system, a discrete system, you want to create a model, and you want to represent your model in form of states, you need to develop the concept of automata theory. You need to have a grip of automata theory before that, because automata theory basically deals with some transition states and some inputs. There will be a state. Suppose at present my state is I am teaching you all, right? So this is my current state. What is the current state? I am teaching. Suddenly my phone rings. This is the input. What is the input? The ringing of my phone is the input. And my state changes to I stop taking the class and I receive the phone call. Try to understand the analogy. My present state was I was teaching you. My present input is a phone call. My next state is I am receiving the phone call. So automata basically deals with this state changes and inputs in a more complex way, and we'll see how it works actually. Okay, so let's start with it. Yeah, so relating with any other subject is very easy. suppose I am talking about algorithm, the subject data structure algorithm. So whenever you're talking of algorithms, it's about how to write an algorithm efficiently. Space complexity, time complexity, all these things become very vital whenever we are learning the subject algorithms. Okay, so you learn at the end of the day to design an algorithm which will enhance the performance of the system and which will work in its most efficient way, right? But in formal language and automata theory, the scenario is something else. It's not about just time and space complexity, but it is about a problem is solvable at all or not. I repeat, in automata theory, it's not about the complexity, it's about if you are given a problem, are you able to solve the problem? Or is the problem solvable at all, or it is not solvable? Now that is a very vital point of automata theory, this solvability. Okay, once you know that the program is solvable or the problem is solvable, next comes the question, how efficiently can it be solved? And then thereby we have different automatas or different machines. The name itself is formal language and automata. So we will deal with formal languages. We will deal with automata. What is automata? Automata is simply, the term means machines. So we have different machines. We will come across 4 different machines with different levels of efficiency, and these 4 machines can accept different formal languages. They have category of formal languages that they can accept. Okay, so once you know that a problem can be solved, next comes which machine will solve the problem more efficiently. Okay, and therefore we can say that this is a study of mathematical systems or machines. Okay, just a second. Okay, so next just definition, kind of a definition of automata. So automata are abstract models of machines that perform computation on an input by moving through a series of states or configurations. As I was talking about, I gave you an example of a state. At each state of computation, a transition function determines the next configuration. So what is a transition function? Transition function is that I am in a present state, I get an input, and what will be the next state. That is a transition function that decides for our automata, right? And this must be known to you. Once we get into the details of the different machines and different automatas, the most general and most powerful automata till date is Turing machine, and we compare Turing machine to modern digital computers, and it is said that if a problem is not solvable by a Turing machine, it is not solvable by any computer. In other words, Turing machine is an analogous to computer, modern day computer. Okay, again, the main objective of automata theory is to develop methods by which computer scientists can describe and analyze the dynamic behavior of the discrete systems. Why? Because we are designing the system in form of states and inputs and outputs, and thereby it will make the process easier to describe the behavior of the system, right? How will a system behavior, how will the state change upon getting a particular input, right? So that is why all these things are the driving agent for learning the subject automata. Okay, so now let's get into the details of how many types of machines or automata do we have. Okay, as I was saying that the formal language and automata theory deals with 2 things. One is formal language and one is automata. So first let's see how many types of machines or automatas are there. Just ignore this part, okay, the grammar part. The first and most powerful machine that we have is Turing machine. Next is linear bounded automata. third is push down automata, and the fourth is the finite automata. If we organize this in terms of power, now what do we mean when we say power? I'm just vaguely saying that my machine is the most powerful one. So how is it most powerful? It is powerful in terms of acceptability. Acceptability of what? Acceptability of language. So Turing machine is such a powerful machine which can accept the maximum amount of languages or strings. To make the thing easier, suppose I know 7 languages. I know Bengali, English, Hindi, German, Chinese, Japanese, Spanish. So I am more powerful than you are. You only know 3 languages. I'm not saying you know 3 languages. It's just an example. Suppose you know English, Bengali and Hindi. So in terms of acceptability of language, you are less powerful than I am. Similarly, here I am Turing machine because I can accept maximum number of languages. I can understand maximum number of languages. I can accept maximum number of strings of that language. So I am the most powerful Turing machine. Next is linear bounded automata, which can accept lesser number of strings of a language. Next, Push-down automata, it's lesser than LBA or linear bounded automata. And next is finite automata, which is the weakest of all and can accept the least number of strings of a language. Okay, so thereby we can classify or we can arrange the machines in terms of their part. And again, as I was saying, that we often say that if a problem cannot be solved by a TM means Turing machine, it cannot be solved by a modern digital computer as well. Okay, so these are the different kinds of automatas or machines. Next, we will move to languages. As I told you, the subject deals with 2 main parts, languages and automata. So I have just shown you there are 4 types of different machines. Similarly, there are 4 types of languages as well. For 4 machines, we have 4 languages. Okay. So, before going into that, what is formal language? Why it is required? See, we human beings communicate using natural languages, right? English, Bengali, Hindi, and we have a lot of things in our language, like besides the words, besides the grammar, besides the sentence, we have gestures, we have sarcasm, we have expressions, and all these things together helps us communicate. So human communication is very, very complex. On a contrary, when we communicate with devices, they do not understand natural language, right? Do they understand English? I'm not talking about voice enabled devices or speech recognition systems. I am talking about normal day-to-day equipments that you use, maybe a fan, maybe a washing machine, maybe a mixer grinder. Do they understand natural languages? No. We have an on and off button and we work with that, right? So for machines, they have their own formal languages. They do not understand natural language. For example, I just said fan understands on and off. So similarly, just as for a fan we have a formal language which consists of on and off, for all the machines that I have discussed till now, that is Turing machine, push-down automata, linear bounded automata and finite automata, we have separate set of languages. That is, a Turing machine understands recursively enumerable language. Okay, a linear bounded automata understands a context sensitive language. A push-down automata understands context-free language, and a finite automata understands regular language. These are the languages specific to a specific machine. Now, one more thing. As I was talking about the power of the machine, so if you remember, finite automata was the weakest. So, finite automata only understands regular language. But if you talk about push-down automata understands context-free language as well as regular language. If you go to this diagram, it will be more clear. Next, see, for linear bounded automata, it will accept or it will understand context sensitive language as well as it understands context free language and regular language. And lastly, for this Turing machine understands recursively enumerable language. It's known as recursively enumerable language. So not only that it understands recursively enumerable language, if you follow this picture, it understands context sensitive language, context free language, regular language and your recursively enumerable language. That's why Turing machine is the most powerful and the strongest machine of all, because it understands all the subset languages, right? But on a contrary, finite automata only understands and only accepts regular language. I hope it's clear, right? So till now, if there is any confusion, before I proceed, I want all of you, please, if there is any confusion, any doubt, because in automata the first class is very, very important, because it's a different kind of a subject, and sometimes you get lost that what is happening, what is a language, what is a machine, everything is going out of my head. So before I proceed, I am telling you repetitively, if there is any doubt till now, if some concept is not clear, concepts will be clear as we move on with our lectures, but still, if there are any doubts that in your mind right at this point of time, please unmute yourself and clarify your doubts before I proceed with the next slides. So is there any doubt, any confusion? Anything you want me to repeat? Okay, so since you are not responding, I'll take that as it's all good and I can proceed. So fine, let me continue with my slide. Yeah, so we have seen machines, we have seen languages. Now what is grammar? Now I do not have to tell you separately that when there is a language, there is always a grammar. Whenever we have started learning the English language or Bengali language or maybe Hindi, we had a separate book, a grammar book, which made us aware of the rules of constructing a proper sentence in English language or Bengali language or Hindi language. Similarly, while we are talking about formal languages in automata theory, we have separate grammars for separate languages, which consists of rules which defines that language. So for regular language, we have regular grammar, or very commonly known as type 3 grammar. For context free language, we have context free grammar, very commonly known as type 2 grammar. For context sensitive language, we have context sensitive grammar, and for recursively enumerable language, we have recursively enumerable or unrestricted grammar or type 0 grammar. Okay, so in a nutshell, I can say that an automata or machine accepts a language that follows the particular type of grammar for that language, right? Now again, regular grammar are the most restricted ones, since again, if we go by the hierarchy of the machines, regular language was accepted by finite automata, and finite automata is the weakest of all, which accepts the least number of strings of a language. So regular grammar in that way is the most restrictive ones. We have like many restrictions while we construct a regular grammar, and on a contrary, recursively enumerable have the least restrictions, and they are we often say that they are the unrestricted grammar. Okay, so you must know this, that regular grammar is the most restricted ones with a lot of rules, and recursively enumerable grammars have a very less number of rules. Now we are going to take this topic grammar in a separate portion, now, just for now, you should know that there are 4 types of grammar: type 3, type 2, type 1 and type 0, each for each kind of a language. Okay. Okay. So next, as I was talking about language, let us dig deeper into the details of formal language and see what actually a formal language means in this subject. So for knowing about formal language, we will come across a few terms. Firstly, symbols. Okay. So symbols are the basic building block of a language. So any character or token can be a symbol. Okay. So let me actually draw the analogy so that it becomes easier for you. So in English language, which are the symbols? Any alphabet, any letter, A, B, S, H, W, anything. It's a symbol. It's a building block of your language. So suppose I am constructing my new formal language, and I decide that I'll have only 2 symbols, 0 and 1. So for my language, I'll have 2 symbols, 0 and 1. Okay. Now this is the concept of symbol. Next comes alphabet. So what is alphabet? Alphabet is nothing but the finite, non-empty, please be very careful about these 2 words, finite, non-empty set containing all the symbols of the language. Okay. So symbols we have already learned. Alphabet is a set, a non-empty finite set which will contain all the symbols for the language. So in English alphabet, A to Z, all the alphabets are there in my set. For my new language which I am constructing, if I have only 2 symbols, 0 and 1, then my alphabet set will contain 0, 1, and this is the sigma symbol which we will use from now onwards to represent the alphabet set. So whenever we will want to define the alphabet set for our language, we will use the sigma symbol and we will just write whatever is present inside our alphabet set. Over here 0 and 1 is there, so I have written sigma is equal to 0, 1. Next is string. What is string? String is nothing but a finite sequence of symbols, or I can say it's a word. For your understanding, if I draw the analogy with English language, it is nothing but a word. So again, concentrate on this part, students. Fruit is a word, right? So what is spelling of fruit? F-R-U-I-T, right? If somebody writes F-R-W-T, it's wrong, right? You know it's wrong. How do you know it's wrong? You might say that it's written in the Oxford dictionary or in some dictionary that the correct spelling of fruit is F-R-U-I-T, and that is what you have learned from your very childhood days, right? Basically it's predefined. There is no rule or there is no law, but it's predefined that this is the correct spelling for fruit. And fruit is something that we eat, right? It's good. There are different kinds of fruits and so on. So the meaning, the value associated with fruit, the correct representation of fruit, all these are predefined. Okay. Similarly, in our new language, we know the only thing known to us is we can use 0 and 1, and we can construct any and every string using 0 and 1. Since I am the designer of my new language, I say that 001 is a string and 100 is a string. 001 means on, 100 means off. You might say that 001 might not mean on. Maybe 000 is on. Since I am the designer of the language, I will decide which is the correct one. Since over here also, you know, same way I was deciding, the spellings are predefined, that F-R-U-I-T is correct, F-R-W-T is not correct. Similarly over here also, I'll decide that 001 is correct and it stands for on, and 100 is correct and it stands for off. That is the standard, and these are my strings. 001 is a string, 100 is a string. Okay. Finally, I come to language. What is language? Language is a set of strings. Language is nothing but a set of strings. For English, I can say it's a sentence. For my formal language, this is a set. So, L is the symbol I use to represent language. So, L is equal to, inside braces, I just write the symbols that are present in my language. So, for my language, I have 001 and 100, which I have decided, right? So, I'll just write them inside curly braces, and this is my language. Okay. So, this is how I can define a language, I can get a new language. Now, why is this understanding important? Because we will gradually move to the different languages, regular, context free, context sensitive. So, before that, you need to know what is a language, what are the building blocks of a language, what is the alphabet of a language, what is the string of a language. This concept should be very clear. Let me give you an example. Suppose there is a language. You have said that there is a language L, right? And L should be a language whose alphabet set is X, Y. So, what do we mean when we say that the alphabet set of a language is X, Y? Meaning all the strings that we can construct for that language will only consist of X and Y, nothing else. Okay? Now, suppose my language says that it contains all the strings whose length is 2. I am not writing it over here. All strings, I'll just write length is equal to 2. Okay? Length is equal to 2. So, my language is such a language over alphabet set X, Y, which will contain all the strings whose length is 2. This is how a language is defined in words, expressed in words. Okay, I repeat, my language is such a language over the alphabet set X, Y, that it will contain all the strings of length 2. So, what will be the content of your language? Try to understand. You can only use these two symbols X and Y, right? So, your language can contain the string X, Y. Your language can contain the string YX. Your language can contain the string XX. And your language can contain the string YY. Is it satisfying the criteria? Yes. Why? Because it is constructed of the alphabet set X and Y, and the length should be 2. So, the length is 2. And do not get confused between this XY and YX. These two are different. Just like when I say I eat, and if I say eat I, these two are different, right? The sequence in which you are arranging your words are different. Similarly, here also XY is different from YX, and so is XX and YY. So, this will be your output language, which contains all the strings of length 2 over the alphabet set X, Y. Clear? See, I need a response. You are so numb from the last 10 to 15 minutes. So, at least please respond.
Yes, ma'am. Yes, ma'am.
Thank you so much. Okay. Next factor about language is a language can be finite or a language can be infinite. So, if you ask a question that is a language always finite? Answer is no. A language can be finite, a language can be infinite as well. So, let me give you an example. So, suppose I tell you that you have a language which is again over X, Y, the alphabet set is X, Y, and your language should contain strings with at least one X. I repeat, your language over X, Y should contain strings with at least one X. Okay. So, suppose this is L2, okay, this language. So, your language can contain X, at least one X. So, X, your language can contain XY your language can contain x, y, y. Your language can contain y, x. Your language can contain y, y, x, and it goes on and on and on. It's infinite because the criteria is at least 1x. Okay, so a language can be infinite. And what is an example of a finite language? This itself is a finite language. Only 4 strings will be there because length is bounded. Only strings with length 2 will be there as a part of the language. But here the criteria was the string should contain at least 1x, and therefore the language becomes an infinite language. Okay, why I am telling you this finite and infinite? You might think that, like, what's the point of knowing that a language can be finite, a language can be infinite? The point is, dealing with a finite language is very easy. A finite automata, which is the weakest machine of all, can easily deal with a finite language because it has some small amount of memory and it can store the language in its finite memory, and it can process the things. But whenever the language is an infinite language, getting an infinite memory is not possible, and therefore finite automata fails to deal with such infinite languages, because of which we went to push down automata, linear bounded automata, and a Turing machine, because finite automata was never capable of handling infinite languages because of the memory problem. It cannot have infinite memory for handling infinite strings, right? Okay, so let's proceed with the presentation. We are done with the formal language. Next, why are machines and automata used? The answer is very simple. Again, this question might come to your mind, that why is ma'am telling us so many things, that machines and languages, like language is something, machine is something else. So why are machines or automata used? So basically, when we will get into the details of automata, we will see that we use a machine or automata to check whether a string belongs to a particular language or not. Just like the example I was showing you, that your language consists of x, 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 y, y, x, and y, y. So we can build an automata to check whether x, x is being accepted by the automata, and if it's accepted by the automata, that means it is a part of the language. Again, we can test the same thing for x, y, or y, x, and if it is accepted, we can say that okay, it's a part of the language. Let me show you an example. Just a second. Yeah, let me show you an example. See, over here my language contains AA comma BB. This is my language. Okay, so in terms of automata, how to define it? See, this is how a finite automata looks like. This is a finite automata, let me tell you. It consists of states. These circles are states and these arcs are the input. So my initial state is Q0. This arrow marks the initial state. So this is my initial state Q0. From Q0 on getting A, I go to Q1 state. From Q0 on getting B, I go to Q2 state. Again, from Q2 on getting B, I go to QF state, and from Q1 on getting A, I go to QF state, and over here QF is the final state. How to denote a final state? It consists of a double circle. Okay, all the states are single circle, this is a double circle. So now, if this is a language and this is the corresponding automata for the language, how to relate both of them? See, you start at Q0, you get A, you go to Q1, you get another A, you go to QF, which is the accepting state. So A, this is accepting. This is getting accepted by the machine, by this machine. Again, B, you go to the final state, which means BB is getting accepted by this automata or by this machine. So we can conclude that this is a correct automata, this is a correct finite automata for the language A, comma BB. Now this was a very simple example. As we move on with our lectures, we will see many complex automata designs, but just to make the thing clear to you, this is how we relate the language to automata. Okay. Acha. Next, another important thing which should be known to you, which I already told you, but still just to repeat, the utilities of the automata. Finite automata is used in lexical analysis phase of a compiler, spell checkers, construction of sequential circuits. Pushdown automata is used in the syntax analysis of compiler, evaluation of mathematical expressions. Linear bounded automata is used for semantic analysis in compilers, and Turing machine is used in AI, neural network, and many more. Okay, so just for your knowledge, these are the application areas of automata. Okay, now, yeah, so we had seen sigma, right? I told you about the significance of sigma. Sigma is the alphabet set of our language, if I am not very wrong, right? See, sigma is equal to A comma B means that our language will have the alphabet A and B, correct? Now there are different representations of this sigma. Let us see the different representations which are very, very important. Sigma to the power 0 is equal to set of all strings with length 0. So sigma to the power 0 is a very special notation which means or which represents all the strings in our language with length 0, and which is again represented as lambda or epsilon. Anyone, either lambda or epsilon represents all the strings with length 0. Next, sigma to the power 1 is set of all strings with length 1. So if A comma B is my alphabet set, and I say that it will I'll have to consider all the strings with length 1, then what will be the strings? Obviously only A and B, because length should only be 1. Again, if I write sigma to the power 2, it represents set of all strings with length 2. Now what will be the set of strings with length 2? AA, AB, BA, BB, right? Similarly for sigma to the power 3, it will be AAB, AAA, ABA, and so on, all the combinations. Okay. Now, finally, this is another very important notation, sigma star or clean star. It is known as clean star. What is clean star? Clean star means set of all strings over the alphabet set given. Over here the alphabet set is A comma B. So clean star here signifies the set of all strings over A comma B. Meaning any combination of A comma B, and it covers this sigma or lambda also. Lambda and epsilon also, that is strings with length 0. So if I elaborate, let me elaborate this for your better understanding. Suppose this is my alphabet set x comma y. Okay, my alphabet set remains same, and I am to design sigma star for x comma y. So my sigma star will contain lambda for null, for 0 length strings. Then I have x, I'll have y, I'll have xx, I'll have xy, I'll have yx, I'll have yy, I'll have x, x, y, I'll have y, x, y, and so on. It's infinite. Sigma star is infinite. Sigma star will contain all the possible combinations of x and y, and it will also contain this lambda or epsilon. Okay. Next important thing is sigma plus. Okay. Sigma plus is very similar to sigma star, the only difference being that it will not contain the epsilon. So if this is sigma plus or positive star, not clean star, it's known as a it's not known as a clean closure, it's a positive closure, sorry. The term was clean closure for sigma star. The term for this is positive closure, and the only difference is that in positive closure we do not have this sigma. It will start from x, comma y, comma x, rest is same. It will contain all the combination except this lambda or epsilon. Okay. So just a second. Yeah. So this is the significance of your sigma. I have already shown you this automata. Achha. Next is understanding language in terms of grammar. Okay. Now this is also a very elaborate or detailed part that we will cover in our next lectures, but just to start off with, again, if your alphabet set is A comma B and your language contains A comma B and you are asked to construct a grammar. See, here you are asked to construct the machine automata you had constructed. Here if you are asked to construct the grammar or to check whether this is a correct grammar for this language, what will you do? The same way, here we had a starting state. Here also we will have a starting symbol represented by S in grammar. Now S will evaluate to capital A or capital B. For now, just consider that capital A is a variable, capital B is also a variable. So my S can evaluate to A or B. This is OR, okay. And what is the value that this capital A is storing? My capital A is storing a small a and my capital B is storing a small b. So if you try to evaluate this expression, see, this is my starting state, it goes to A. A can be replaced by small a and a small a. This means that S tends to small a and small a, which is part of a language. Again S tends to capital B. So capital B contains a value B, like small b. So S tends to small b. So S tends to both small a and small b, which is the part of my language and which actually signifies that my grammar is correct, or this is the corresponding grammar for this language. Okay. So I will not start grammar today, like in details. I will start grammar next day. In the next class we will learn how to write grammar for a particular language, how to design a grammar for a given language. Okay. So this was all for today. As always, you know, you have your IMCRP test, the code of which is already given. Okay. So yeah, if you have any problems, please unmute yourself and ask. Otherwise you can leave the meet and you can please go and give the IMCRP test. Okay. So we will be meeting in our next class with the details of grammar. Okay. Thank you.